Hello everyone, welcome to Taylor's Classical Mechanics. This is going to be problem 4.24 in the textbook. So I'm going to go through and kind of read the problem statement and then we'll kind of get started on the solution. So problem 4.24 is stating that we have an infinitely long uniform rod that has a mass per unit length of mu and is situated on the z-axis. So we just have an infinite rod going up and down the z-axis, and it has a mass density of mu, a uniform mass density. It wants us to then calculate the gravitational force, F, on a point mass, M, at some distance rho from the z-axis. So we have some point mass, and we're using the cylindrical coordinate rho to denote some, horizontal distance from the rod. So you can kind of think of my pen as the rod, and then the point mass could be some distance rho. It could be anywhere around some radius, right? So given some distance rho, it could be anywhere on that circle of that radius rho. But we want to calculate what the gravitational force is on that point mass. And then it says rewrite the force in terms of rectangular coordinates of the points x, y, and z and verify that the curl is 0 to show that it is a conservative force, to show that the gravitational force is conservative. And then also show that the curl is 0 by expressing the curl in cylindrical coordinates, and then find the corresponding potential energy U. All right, so I'm going to start off here kind of with a diagram of the problem. So we have our z-axis going up and down. So x right now is coming out of the page. Y, well, I wouldn't really think of x and y, and I guess in this case, just think of the z-axis and then think in terms of cylindrical coordinates. So this distance rho, so this is our point mass m. This distance rho could be anywhere around the, if this was our rod, this distance rho could be anywhere around. So I'm kind of just generically drawing, rho as some distance away from the rod, but I'm not necessarily, it lies, in the XY plane, but I'm not necessarily saying it lies on the x-axis or on the y-axis or something. So let's just kind of go over definitions here. We have this point mass m, this distance rho from the rod. The origin is kind of at the, I guess, the center, but the rod is infinite, so it goes infinitely this way and infinitely this way. And then I have this distance r that points to some differential amount of length on the rod. So that I've shaded some region here, which is dz, which is like a differential amount of length on that rod, and we're going to use that. And so that distance r is the distance from some differential amount of length on the rod to our point mass. And then I drew the angle alpha here as the angle between this vector rho and then this vector r. And then I drew this df, meaning like this is the differential amount of force that this piece of the rod, this tiny piece of the rod, exerts on our mass. And it's a gravitational force, so it's pulling the mass towards the rod, so it points this way. And then the rod has a mass density of mu, so just some constant, mass density, which is kilograms per meter. So this is kind of similar to like an electrostatic problem in a way, except just working with the gravitational force. So the differential amount of force produced by this little piece of the rod is going to be the gravitational force. So we have, the gravitational constant times the mass of the point mass times mu dz, which this is the mass per unit length times a tiny amount of length, which gives mass. So this is the mass of this tiny amount of the wire, or sorry, the rod. So this is the gravitational constant times the mass of the point mass times the mass of the rod divided by r squared, right? That's just the magnitude of the force. And we know that the direction of the force is going to be, in that direction. Now, by symmetry, we know that the rod is infinite, so it goes in both directions. So if you think about, there's a piece of rod up here that pulls it this way. There's also if you found the equivalent piece of rod the same distance on the other side of the origin, it would be pulling it this way. And you could argue that across the entire length of the rod. So anywhere above the origin, you could find an equally symmetric piece of the rod below the origin that would be pulling it in the other direction. And so basically, if you drew out those vector components, all of the only component of the vector of the force that doesn't cancel out would be the force going in this direction. So like this dF can be expressed as like two components, right? You have the vector this way and then the vector up. Like all the up vectors will be canceled by a down vector due to a force from a piece of the rod this way. So all of just by symmetry, the force should only be in this sort of rho direction, which is like along the line connecting the rod to the point mass along this rho vector. So that's just an argument by symmetry. I'm not going to really prove it, but as a physicist, a lot of your arguments and things come from symmetry. So we're going to leave it at that. So the differential amount of force in the rho component of the force here, which would be this vector here, would be minus, and I guess I'm doing this, the minus is because I'm wondering if I forgot a minus sign here. I don't think so. There shouldn't be a minus sign here. I imagine the minus sign here. I guess it's just because it's in the minus rho direction, I guess. So that's where the minus sign comes from. But the magnitude is still going to be the same, so it's Gm mu, but if this angle is alpha, then cosine of alpha, then the rho component, this vector here, right, is going to be, let me kind of draw out this thing a little bit more clearly. So, right, like this is alpha, this is dF, this is dF sub rho, and this is like dF vertical, I don't know, right? That's the vertical component of the gravitational force. This is like the rho component of I guess this would be the Z component, right? The Z component of the force. And so cosine of alpha, like this component d, if like cosine of alpha is equal to opposite over hypotenuse, so dF sub rho over dF. So dF sub rho is just dF times cosine of alpha. So we take this and multiply it by cosine of alpha, and so that's what I've done here. And then add the minus sign over r squared. So that's basically what I've done here. We take dF and then multiply it by cosine of alpha. And then I note again that cosine of alpha is also rho over r, because this vector, this length here is r, this length here is rho. So we can also write cosine of alpha as rho over r. So I replace cosine of alpha with rho over r, and we get minus Gm mu rho over r cubed because of the extra r term on the bottom, dz. So this is going to be our expression for the differential amount of force produced. And then to get the total amount of force produced, we just simply integrate it. So we're going to take, the total force F sub rho is minus Gm mu rho. These are all just constants. And then the integral from negative infinity to positive infinity, right? We're integrating z from negative infinity to positive infinity across the entire rod. So this will be 1 over r cubed dz. Well, we need to express r in terms of z. So we have minus Gm mu rho, and remember rho is a constant. Well, from this diagram here, r, the hypotenuse of this triangle, is just z squared over rho squared, right? This distance of the triangle is just z, however high this piece of rod is. So we can write that as z squared plus rho squared. The square root of that, right, is r. But r squared, well, we have r cubed. So the cube of the square root gives us this to the 3/2 power, essentially. So that's why we have it to the 3/2 power. Now, this integral is a bit tricky. It's basically a trigonometric substitution integral. And to solve this, you can let z equal rho tangent of u, or whatever you want your angle parameter to be. I just used u in this case. And then u becomes arctangent of z over rho. And then dz, if we take dz is just rho secant squared of u du, because the derivative of tangent is secant squared. And so we can replace dz here with this, and then we can replace, z squared is going to be rho tangent, and then rho is just rho. So we can plug in our substitutions into this integral, and we get minus g mu rho, integral from negative infinity to positive infinity. And I should have changed these bounds. I didn't change these bounds until the end, but I'll talk about that later. Really, these bounds should be pi over 2, or negative pi over 2 to pi over 2, because, well, you'll see why in a second. Essentially, it's because the arctangent, our u, which is our new, the arctangent itself, if you graph that function going to infinity on both sides, it has asymptotes at pi over 2 and negative pi over 2. So our original bounds going from negative infinity to infinity, when plugged in with our substitution, becomes negative pi over 2 to pi over 2, because when you go out to infinity with the new function, it asymptotes out there. So that should be our new bounds. But so plugging in this substitution, we get rho secant squared on the top of u, and then rho squared tangent squared of u plus rho squared, all to the 3/2 power du. And then we can simplify this even more, because we can pull out the rho squared and from here, and pull that out, and we'll have rho over rho squared. So those will end up canceling. I kind of keep it there, and we're just left with secant cubed on the bottom, because tangent squared plus 1 is secant squared, I believe. So let me just double check. Did I write that down? I believe I need to double check, because when you factor out rho squared, you're just left with tangent squared of u plus 1, still to the 3/2. So you're left with, secant, the square root of secant squared is just secant, but then you're left with secant cubed. So tangent squared plus 1, I think, is secant squared, but then when you take the square root of that, you're just left with secant, and you still have the cubed, so you're left with secant cubed on the bottom. And then eventually, and then I pull the rho out up top, so that's what's happening here. I think I might have forgotten to square rho or something. I might have messed up a factor of rho here, but that, I'll let you guys figure that out. But obviously these are going to cancel out, and we're going to be left with 1 over secant of u on the bottom. So we still have negative g mu rho over rho squared, 1 over secant, and 1 over secant is just cosine. So our integral is just the cosine. We're integrating cosine of u, which becomes sine. The integral cosine is sine. And again, I had to change the bounds of the integral, because we were not integrating from negative infinity to infinity, but the bounds change after our u substitution, or our trigonometric substitution, to be negative pi over 2 pi over 2, which means that, sine of pi over 2 is 1 minus negative 1, because this bound sine of negative pi over 2 is negative 1, so we get 2. So then we get a factor of 2 on top. So our force ends up being negative 2gmu rho in the rho hat direction. And this is correct. This negative sign is correct because we know the force is going to be in the negative rho hat direction if we define rho to be like positive rho to be this way. And I kind of talk about the bound change, and I kind of drew a rough sketch of what like the arctangent function ends up looking like. So that's that. So this ends up being our force. So that's part A. Part B requires us to write our force in Cartesian coordinates, which is not hard. Right now, this force right here, this is written in cylindrical coordinates, rho, right? Our cylindrical coordinates are rho, phi, and z. But if we kind of look at a top-down view, so this is like z is like this, and then this is the xy plane. Rho is just, and we define some angle phi here from the x-axis, which is how we define it. Then rho hat can just be expressed as, this is cosine of phi over here, this is sine of phi over here. So rho hat is cosine phi x hat plus sine phi y hat. So cosine of phi is x over rho, sine of phi is y over rho. And so we can plug in this expression for rho hat, and we get minus 2g mu over rho squared, and we get x hat plus y hat, and then no z hat component. And we can note that rho, this vector, is just the square root of x squared plus y squared, right? This distance is x, this is y. So we're just using these conversions between basically polar coordinates and Cartesian coordinates to get this vector here. Now, the third part asks us to, well, actually, now that we have the force in Cartesian coordinates, this is still part B, we need to prove that it's conservative by proving that the curl is 0. And I, again, just wrote down, if you look in the back of the book, you can find the curl, but essentially I have it written here. The curl in Cartesian coordinates is expressed like this. So our force only has x and y components to it. So if you look, like, this component is 0. There's no z, so anything with respect to z is going to be 0. So there's no x component to the curl. There's no y component to the curl because the x component doesn't depend on z, and there's no z component to the force, so this is 0. So we're only going to have a z component to the force. Excuse me. I'm a little under the weather, so I'm trying my best here. But essentially, the z component of the force is just going to be the derivative of the y component with respect to x minus the derivative of the x component with respect to y. And just looking at our force from before, the derivative of the y component with respect to x is going to be, well, that's not the right one. Sorry, I picked up the wrong pages. Here's our vector here. So the derivative of the x component is x over rho squared, and the y component is y over rho squared. The x component is x over rho squared, because remember, rho does have x and y in it, so it needs to be a part of the derivative. And when you take the derivative of, with respect to x, of y over the square root of x squared plus y squared, you get this. So this obviously cancels. And then when you take the derivative of this with respect to y, you get this. And what you find is you have the exact same thing. So when you take the difference between them, you're subtracting them, right? When you do the curl, you do the subtraction between those two partial derivatives, you end up getting 0. And what you find then is that the curl obviously then is 0. All three components of the curl are 0, so the force is conservative. Now this is even easier in cylindrical coordinates, because if you look at the curl in cylindrical coordinates, well, we already know what our force is in terms of cylindrical coordinates, because that was what we found originally. And if you look at the back of the textbook, I believe, there is expressions for the curl in Cartesian, spherical, and polar, or polar and cylindrical. Yeah. So our original force in cylindrical coordinates is this. It just has a rho hat component. So if you look at the curl, there's no z component, so that's going to be 0. There's no phi component, that's 0. So there's no rho component to the force, to the curl, I mean. And then for the phi component to the curl, well, we do have a rho component, but it doesn't depend on z. So that's going to be 0. And then there's no z component, so that's 0. So there's no phi component. And then the z component, well, there's no phi component to our force, so that's going to be 0. And we do have a rho component to our force, but it doesn't depend on phi at all. So the derivative with respect to phi is 0. So it's very easy to just show with some simple, just like observing, that using the formula for the curl, there is no component of the curl on any of them. So it's also 0 by using the cylindrical form of the curl. All right, so for part D, we need to find the potential from the force. And we know that the potential function is given by negative the integral of, from some reference value to our final value of the force dotted with dr, where the force is obviously our force, and dr is, the direction that the path of our path for whatever path we're going on. So for our example, we're going to let our reference r naught be rho naught, phi naught, z naught. So it's just going to be some point in space that's going to be our reference value, and we're just going to denote the reference point as rho naught, phi naught, z naught. And we can define our integration path. Since the force is conservative, it's independent of the path, so we can choose some convenient path that makes our integration simple. So we're going to find, from our starting point r naught, we're going to go parallel to the z-axis, so we're going to go up some amount z to where, from our original z naught to whatever our final z is. So our first path is going to be the path along that z line. So there's going to be no movement in the phi or rho direction. Then we're going to circle around. So we're going to move up, and then we're going to circle around in a circle some amount from our phi naught, our current phi naught, to some amount, wherever we want to go to our final phi value. So we're just going to move in a circle until we get to that phi value. And then we're going to move out radially and from our original rho naught to some value rho, our final rho value. So we're going to basically move along each of the unit vector directions for the cylindrical coordinate system, starting from our reference point to our final point. Now, the force only acts in the rho direction, right? If you recall, in cylindrical coordinates, our force is negative 2g mu over rho in the rho hat direction. So our force only acts in the rho hat direction. So along these first two paths, the force is in rho hat direction, but dr for the first path is z hat. And then dr for number 2, our number 2 path is in the phi hat direction, but the force is still in the rho hat direction. So the dot product between the force and dr is perpendicular. The directions are perpendicular for the first two paths. So we know the dot product for any two vectors that are perpendicular is 0. So the force does no work when we move along the z direction, like solely along the phi direction. But the force will do some work when we move along the rho hat direction. And so we know the force and dr are both in the rho hat direction. So if we do our integral for the last path, the third path, going from rho naught to rho, we have the negative sign due to this equation here. And then the force is negative 2g mu over rho. And then so F dot dr is basically dr in cylindrical coordinates is just d rho for the rho hat component. So we're dotting the rho hat components, and this is what we get. Everything here is a constant except for the rho. We're integrating with respect to rho, so we're just integrating 1 over rho, or 1 over x. And the integral of 1 over x is just the natural log of x. And when we plug in our bounds, we get the natural log of rho minus the natural log of rho naught, which can just be expressed as the natural log of rho over rho naught. So our final potential function is the negative sign here cancels the negative sign out there. You get a positive 2g mu natural log of rho over rho naught. And that is our final potential function. All right, thank you guys for watching. If you guys enjoyed this video, please let me know. Leave your name in the comment, or leave a comment below. Let me know if there's any errors or anything here. So I really appreciate you guys watching, and I'll see you guys on the next one.